for the next afternoon session. We actually have three speakers, two of which I've got down listed here. One is Joe Stanley, an embedded hardware and software hacker who's been seen at LCA over the past decade with OLPC, laptops, rockets, balloons and lots of other things. He will also give a more elaborate introduction. And Mark Jessup, who's an electronic engineer, PhD student at the University of Adelaide, who's involved in a thing called Project Horus. The title of this presentation is Tux in Space, because we certainly need to get Linux all over the planet and off the planet. So can we please give a very warm welcome to Linux Conf Australia 2012 to the speakers on the topic of Tux in Space. Thank you.
It's going to show a video. We're just going to begin with a quick video, which highlights a bit of what we've been doing in the project.
And we have no sound on the video. Can we get sound for the video? Yep, there's no sound.
Just play that. Yeah, so it's going to do. We're going to hold the microphone up to the laptop speaker because we haven't actually got working sound. Add that to the list of things that aren't working today.
We're not AV guys.
Where's the speaker?
We're actually much better at launching the balloons than playing videos.
Hi everyone, I'm Terry. As I was saying, I'm Terry. I didn't actually get an intro in the beginning, but I was the founder of Project Horus, and I'll be speaking to you a little bit about how the project got started and what's involved in the launches, and then my colleagues here, Mark and Joel, will take over and talk a bit more about the technical aspects. Can I get the next slide? All right, so we started the project back in 2009. Myself and a couple of friends had sort of seen this kind of thing done online. There was one particular group that achieved a bit of notoriety, some MIT students who did this on a very low budget. We saw this and thought maybe we can achieve the same sort of thing, hopefully on the same sort of budget. It turned out that the budget thing wasn't really going to be possible. But since 2009, we've been launching fairly regularly, every month or two, and so far we've racked up about 20 launches. We've now got about half a dozen folks who are involved on a regular basis, and we sort of come from all different kind of backgrounds. There's hobbyists amongst us like myself, and then we've got professional engineers, electrical engineering students. Both Mark and Joel at the time of the project beginning were both studying electrical engineering, and amateur radio enthusiasts on board as well these days, which certainly helps out with the radio side of things. One of the questions we get asked quite a lot when we do this is why we do it. The main reason for us doing this is that we find it fun. It's a challenge, it's something to test our skills and see what we're capable of. Initially, when we first launched the project, the goal was to get a camera up to about 30-35 kilometers, capture some stills or video, and really just see what we could do. Since then, we've really grown, and my microphone seems to be a little dicky today, but we've really grown, and we've flown all kinds of experiments since. We've flown a bunch of amateur radio repeaters, flown video and stills payloads, and certainly hoping to fly a lot more in the future.
So I'm going to talk a bit about how we go about launching the balloons. On the right, on the screen there, you can see a balloon in flight just after launch. At the top is a rubber latex balloon. So we fly balloons that range in size from 2,000 grams down to 100 grams. The weight is the uninflated weight of the rubber latex before we put the helium in it. Below the balloon there, you can see the radar reflector. So that's there to make sure that airports and whatnot can see where our balloons are as they go up. And below the radar reflector is a parachute. The parachute's not there to stop it from falling, but just to slow it down a little bit, so as the payload hits the ground, we don't get broken cameras and smashed payloads, because we like to recover them. So below there are the important parts, the payloads themselves. So it's a foam box, styrofoam box, stuck together with duct tape. And inside are the little flight computers and the cameras that we use. The reason we use styrofoam is because it gets pretty cold up there. We've measured down to about -50, -60 degrees Celsius, but we know that it gets a bit cooler. Our temperature equipment starts screwing up before that. And it's all literally held together with string and duct tape. So the line you can see there, even though it looks quite thick here, is very, very thin line. And then the payloads are stuck together with duct tape and super glue.
So, on the topic of payloads, as Joel mentioned, they're really the most important part of the payload, or the part of the balloon, I should say. Without the payloads, we don't recover any useful information, and certainly we can't track our equipment. So, the very most important payload that we fly is our telemetry payload, which we've gone through a few revisions of, but essentially remains pretty similar to what we've been flying since day one. It's designed to be as simple as possible, as reliable as possible, and to continuously transmit the position of our balloon. We'll talk a little bit more about the individual payloads that we've used as we go through the slides here. And I would ask that if you do have any questions, feel free to raise your hand. We'll try and take maybe 1 or 2 questions per slide, rather than doing it at the end. Now, something else that, as I mentioned previously, we've flown a bunch of times on our launches are cameras, both video and still cameras. With our still cameras, what we usually use are Canon PowerShot cameras running a customized firmware called CHDK, which is the Canon Hacker's digital toolkit. Lets you script the cameras to do things like take a photo every X seconds, all the way through to motion detection, taking photos when the camera detects motions. It's really quite powerful. For our video, we primarily use the GoPro HD Hero cameras. These are targeted at extreme sports enthusiasts. They're designed to be pretty rugged, which suits us really well. We've had pretty good success with them. Early on in the piece, it seemed that they had some firmware issues. They're really designed to only record for short periods of time rather than the 3 or 4 hours that we often put them through on a flight. So we need to supplement their batteries because they go flat after an hour or two. And we also had issues where they were hitting their file size limit and weren't successfully rolling over. So our video would just cut short after 4 gigabytes, the FAT32 file size limit. We have experimented with other little video cameras. You can buy these all kinds of cheap Chinese video cameras on eBay. Most of the time they're not really worth mucking around with, though. We find that the better cameras are certainly worth the risk, and we have killed a few, but we think it's worth it. Other payloads that we've flown, as I mentioned previously, we have flown amateur radio repeaters. We've flown 2 separate repeater payloads, one of which was a simplex or talkback repeater, which would simply record whatever was said to it and then replay it. Given its elevation and position, it had great coverage when it repeated what was said. We also flew a talk-through repeater with which we logged contacts from rural South Australia all the way through to the Mornington Peninsula and New South Wales, and I think even we got a contact or 2 in Canberra as well. So certainly the question was, do we use APRS? And yes, we do. We'll actually touch on that later on, so we'll leave that for then. Something else that we've flown more recently, I suppose, has been art installations and things like the Tux doll that we flew last year before the 2011 Linux Conf. If you were there, you might have seen the video in full. We recently flew something similar, a plush monkey that was for a video clip for a band. And we flew a yo-yo for some promotional work and a statue for an art installation. So the payloads are certainly quite varied. Sure, so the question was, with regards to the payloads, how much weight can we carry? And would it be beneficial if we use hydrogen instead of helium? On the hydrogen topic, yes, hydrogen does have slightly higher lift, slightly better lift for a given volume, but it's also more dangerous. It's flammable. There are safety precautions that have to be taken into consideration. It is, pardon me? Yeah, don't smoke when you're doing it. That's a good idea. No, in all seriousness though, we have seen what the Bureau of Meteorology do when they work with hydrogen, and it makes us a little bit wary. Even though it is cheaper, we do avoid hydrogen. We use helium just for the safety side of things. On the topic of weight, it's really limited by how high you want the balloon to go and how quickly you can go. As a rough sort of guide, usually you work around the 1 kilo mark for a launch. Just take one more question. Usually we just rely on burst. We have used cut-down systems where we have resistive heating elements that melt the line. We use nylon lines, so they cut it pretty easily.
All right. So, what are the common features that we normally want to fly on a telemetry payload? Well, we want to know position, of course. Most important thing. So, a lot of GPS modules are actually height limited. This is a regulation to stop you from making missiles using them. And we use a particular brand of GPS module called U-Blocks. These don't have the limitation, and they've worked very well so far. For our transmitter, we use a small module by a company called Radiometrics, about 25 milliwatts output power, not very much. And we also have other sensors. So, for example, we always fly two temperature sensors, one inside the payload, one outside. It's always good to have a look how warm your payload's getting due to regulators and so on and so forth. And it's great to see how cold it gets. It gets really, really cold, around about 12 kilometres at the tropopause. Now, on the topic of cold temperatures, batteries. Everyone knows what a LiPo is. You've got them all in your phones. And you think we'd use them. Great energy density, they're so light. They don't work below about -20. When they freeze, they stop working at all. So we actually use Energizer lithium AA batteries. These are primary cells, one use only, but they're extremely light as well. Great energy density, And yeah, we've never had any problems with them at all.
What you can see on the slideshow here is a photo of one of our very first telemetry payloads. Some of you might recognize that it's an Arduino board at the bottom there. The payload was based around an Arduino with a GPS shield on top of it, and the shield on top of that, which was piggybacking on top of the GPS shield, has a radio transmitter, which is the module up towards the top. It also has a low dropout voltage regulator on the left-hand side that was used to replace the Arduino's regulator, which wasn't performing at the level we wanted. And there's a GPS patch antenna on there as well for the GPS. So this worked, but it's a bit heavier than what we were hoping for. So the next revision of the payload was this. This was the so-called NUT board. NUT coming from the same lineage of names as Horus. For those of you who are familiar with Egyptian deities, you might know what I'm talking about. Again, we stuck with an Arduino-compatible design. It's using an Atmega 328 processor. Everything is all on the one board here, and it was etched at home. It was designed so that it could be easily etched and reproduced if needed to be, because we figured we might lose them. No, what you see there is not the antenna. There are some fly wires coming off, one's for battery and one's for a temperature sensor, but no, you don't see the antenna, other than the little black knob on the right-hand side, which is the GPS antenna. Now, we have moved to much smaller payloads since, and Mark's actually going to talk about his latest payload.
So I was over in the UK for quite a while, as some of you may know from my talk yesterday. And on the weekends, I got reasonably bored. And one weekend, I got so bored, I decided to redesign the telemetry payload. And I made a SMD payload, micronut. So nut, but a heck of a lot smaller. You can see the size of it on the screen there. It's no bigger than a AA battery, pretty much. So it has all the same features, GPS, and you can see I've labeled some of the parts of the board, temp sensor, transmitter, so on and so forth. But it weighs less than 50 grams. And this is important. There is a CAS regulation which allows you to launch payloads under 50 grams without any prior approval. So very light payloads. And yes, of course, onboard GPS, and you can see the GPS antenna at the top there.
I'm going to talk a little bit about the software that we're running. First, with the software that runs on the embedded devices that are flying as payloads. So they're all running Atmel ATmegas, essentially Arduinos. We use the Arduino IDE for writing most of our code. With the newer boards, they don't have the bootloader on them because we use ISP headers to program them, because we have to also connect the serial port to the GPS. So it reads the GPS and sensor data and then constructs a string to be sent back down to the ground and also logged to an onboard storage. This string is kind of standardized amongst people who do hard-to-tube balloon gear. So we have the call sign, the name of the launch, a sequence number that always increases, the UTC time, which is coming from the GPS. GPS also provides position, altitude, and speed, and also the number of satellites it currently sees. That's important for when we're launching. We want to know that when it's on the ground, it's getting nice clear coverage to the skies, and it can maintain a lock as it goes up, because GPS is all we use to know where it is as it's on its way up. Yep. Question on GPS? Yep. So the question was, some modules have limitations on how high and how fast you can go. We don't go that fast, and with the height, we haven't encountered any restrictions so far. We use the u-blox GPS modules, and they continue working all the way up to about 35 Ks, which is the highest we've gone. I'll get you to direct that question at Mark when he's back on stage. Thanks. So we also transmit temperature and sometimes battery voltage, just to keep an eye on how the health of the payload's going. So we send that back down using what's called RTTY modulation, radio teletype. I'll rewind a little bit. The modulation is actually FSK, frequency shift keying. It's quite basic, only one step up from on-off keying from Morse coding. So you can see there's two frequency tones, and we shift between the two, with the higher tone being a 1 and the lower tone being a 0, with a very small separation between them. And so that's a capture from a real payload you're seeing there. Below it, the 1s and 0s are then grouped up. So from the green start bit to the red end bit, that's an 8-bit ASCII number. which translates to an ASCII number. And so there we're sending VK5 across the air. Skip. So the software that runs on the ground, we have ground stations that record the software and then upload it to a website, so we can have distributed listeners all around the country, which is great for when we're driving off in our cars, driving under trees and whatnot. It's also good for having a number of sites. So as the balloon goes over certain areas, the signal strength or the ability to decode the signal gets degraded. So it's good to have a diverse location of receiver sites. So FLDigi is a pre-existing bit of open source software for decoding different types of modulation schemes. We have a modified version called Distributed Listener, FLDigi, that's designed for doing high-altitude ballooning. And so that receives and decodes the RTTY data that I showed just before using the line in on your PC and uploads to a website that uses a CouchDB backend. That data is then consumed by Space Near Us tracker. So that's a Google Maps page that plots the location of the balloon. It also plots the location of the cars and the receiver sites around the country. So people can see their name popping up there and the packets that they've contributed as they upload data for us. So, we also upload the current position of the chase cars. That's good for when we've got a couple of cars chasing the balloon. We know where each other are. We might take different rows to try and beat each other to the payload. It's also interesting for the people at home. They can sit there barracking for the red car or the green car. So just as a backup to this web-based system, because we're going out to regional South Australia quite a bit, sometimes the 3G coverage isn't that crash hot. We have an in-car tracking system that calculates the predicted landing site of the balloon using a complete offline system. The reason it's just a dot point down the bottom is that's currently relies on some Windows software. So if anyone wants to re-implement it for us, come talk to me afterwards. So this is an example of Space Near Us, the tracker website. The green circle there, that's the 5-degree elevation line. So if you stand on that line and look up at the sky, if you had infinite vision, you could see the balloon 5 degrees above the horizon. And the radial lines coming out, they're the receive sites that have currently sent that packet back to the website to be displayed. So that's a pretty impressive bit of receiving there. We're using 25 milliwatts. So about what a little LED is going to push out in terms of light emission. And so the fact that we can get from one side to the other of Southern Australia is pretty cool. We were going to do an FLDigi demo, but because we had to switch to a Windows laptop, that's not going to happen. Sorry about that. Mark?
So, as was asked before, yes, we do use APRS as backup. We've begun to use it a lot more recently, just because we've managed to make the payload, so the Micronaut board will work with APRS. So for those that don't know, and I think Bruce talked about it this morning, about APRS, it's a very low bandwidth, well, low baud rate, almost like a multicast network. Packets are repeated and go out on the web, and eventually they can be gated to the web. So at the bottom here, there's kind of a diagram of how it may work. So you might have a transmitter which transmits a packet, a digipeater will receive it, it will repeat the packet, another digipeater may receive it again, and then eventually it'll reach an iGate where it goes onto the web. And it can be, and all the data can be visualized using some quite interesting web services. There's a very useful website called aprs.fi. So as you can see, this is a kind of a display from aprs.fi, so you can see it showing the balloon track, and the lines here show their packet path. So the balloon's broadcast a packet, it's been received by the digipeater in the lower left-hand corner, and it's been received, and that repeated packet has been received by an iGate at VK5EX.
One of the reasons that I've just been off stage there is related to what we're doing here. This is a picture of a prediction that's been run for a launch from the LinuxConf as of today, with today's weather. So something that's always important for us is to know where our balloons are going to go, roughly. We can't launch, obviously, if they're going to go in the ocean or if they're going to go in places that people might get annoyed, like military restricted airspace. For that reason, we use prediction models that let us work out with a fairly good confidence interval where the balloon's going to go. The prediction software itself is written and maintained by some teams at Cambridge University. Some of the students there started writing this a few years ago. The software uses models that come from the NOAA, the American National Oceans and Atmospheric Administration. They provide worldwide atmospheric models. Various sections of the world have varying levels of detail. Fortunately for us, we get decent detail here. And these models enable us to essentially simulate the balloon's ascent and descent through the atmosphere. Coupled with our input parameters, we can then get an idea as to the path it's going to take and where it's going to end up. The NOAA models are released every 6 hours, so there's a new data set every 6 hours, and they're released for about 7 days in advance, which means we can sort of forecast or simulate a balloon launch up to a week in advance. Obviously, the closer we get to the day, the more accurate our simulation is. But assuming that we get our input parameters right, our ascent rate, our descent rate, our burst altitude, that sort of thing, then generally the prediction is pretty accurate. It's enough for us to know roughly where a balloon's going to go, if it is going to be suitable for us to launch or not. What you can see here is a couple of photos of us getting ready to launch, just like we've been doing behind the stage at the moment. We're not launching as large a balloon as you can see there, but hopefully something that's enough to give everyone here an idea as to what's involved with a launch.
So once we've launched our balloon, we want to get the payload back. So we've got chase vehicles fitted out with car computers, lots of radios, and of course lots of antennas. As you can see in this picture here, we've got high gain antennas for when the balloon's low on the horizon. We've got some lower gain antennas when it's kind of above us. And we've also got directional antennas. So if all else fails, say if our microcontroller crashes for some reason and we still have a carrier being broadcast, we can spin the antennas around and find a bearing. And of course, and this is my seat. This is where I sit during a fox hunt. Now, it's also good to have four-wheel drives because, well, this is what happens if you don't have a four-wheel drive.
Notice Terry just left the stage.
Yeah, that was Terry's car. Also note, four-wheel drives are not infallible. Yeah. So
yeah, Mark and I, our first launch was Horus 8 back about a year ago. Horus 8 was a particularly special launch because Mark had been working all year on his final year project. Do you want to tell us a little bit about that, Mark?
Well, I was working on a HF telemetry transmitter, which was originally going to be placed in the Antarctic for use for some ionospheric research measurements. And of course, it has to work in very cold temperatures. Well, it's cold high up in the atmosphere, so I figured let's put it underneath a balloon and see what happens.
So Mark spoke with Terry and got approval to do this, and we went ahead with organising a launch. So we got there on launch day and started filling up the balloon, as always. There's a particularly critical part when you're filling up a balloon, and that's when it's full of gas, but you haven't tied off the neck of it yet. It slipped. It's a short story. So luckily we were inside. We always prepare our balloons inside. So it bounced around the roof and leaked out most of the helium. But we had just enough to fill it back up and get enough lift that both Mark's payload and the Horus payload, which would be the primary payload, could go up into the sky. So we knew it was going to go pretty slowly, which is a bit of a problem. It means there's lots of waiting around. So we got the barbie on, got the beers out, and started waiting. So several hours elapsed. We jumped in the cars and started driving. Things were going okay. It hadn't burst yet, though. And then someone observed that it hadn't gone up for a while. So the way our balloons come down is they keep on going up until the external pressure gets so low that they've expanded so much they burst and come back down. But if you've only got a tiny bit of lift, sometimes they get to equilibrium and they just float. And that's the technical term for it. So our balloon was in float. And that was okay, because it was still going to land on the ocean. There's wind inversions as it goes up. So even though it had started to travel off the coast towards Kangaroo Island, we knew it was going to come back on land, and we were relatively confident. Mark was pretty pale, though, worried about his poor payload, because he still had to present it at the University Expo at the end of the week. So we were driving towards the balloon, towards the coast, and it's getting closer and closer and closer to landing on the coast. And we jumped out the car, and over it came and splashed down about 50 metres out. If you've got really keen eyesight, you can see it starts to go a bit jaggy on the screen. So just before the jaggies is where it landed, but there was a nice strong offshore breeze, and that's the reason it didn't land on the shore. And so this offshore breeze started carrying it out. One of our colleagues tried to get in the canoe and grab it, but he got dunked pretty quick, so that was the end of that. And meanwhile, it turns out Terry used to be quite a competitive swimmer, and so he'd stripped off and jumped in and was halfway out there. But he hadn't told many people that he was out there, nor that he was a good swimmer. So we were getting a bit worried. The local CFS bloke had put the squad on standby, and he'd come down with a paddle for the canoe. So I jumped on the canoe, went out there, and we managed to rescue the payload. Terry was fine. He was towing it a bit like a sea anchor. The parachute was dragging him along nicely. So here you can see Terry on the left, and then the payload dragging on behind me on the canoe. As I said before, there was a nice offshore wind, so that was fun. And the sun was setting as well, so time was of the essence.
How much of it worked after that?
Mark's going to fill you in on that. So this is me carrying the payload back into the shore.
So of course I'm seeing Joel walk onto the shore with my final year project. So I get it from him, tear it open. And so we're using these lithium primary batteries, and they're fizzing. So this is I think it had about 6 ampere hours of capacity in there, and it's fizzing. And I'm thinking, oh dear. So I take them out, throw them away. The board survived though. There was quite a lot of saltwater corrosion. That didn't go too well, but the board still worked. Now the other payload, on the other hand, so below my payload was a telemetry payload. That survived. There was also a GoPro camera in there. That got doused in salt water. Now GoPro cameras don't like salt water. We got the video back. We didn't get the camera back.
Video though, did we?
No, this was the flight where we had the firmware issue, so it cut out after the first 40 minutes. We weren't very happy about that.
So you didn't use the enclosure, the waterproof that comes with?
The problem we had was we had to get the power. We had to get extra power to the GoPro. We had to have a hole in the side of the enclosure.
GoPros tend to be used by people like jumping off buildings and recording the 3 minutes it takes to get to the bottom. And so when you're doing an 8-hour balloon flight, they tend to go flat. So we had to have an external power source for the GoPro. Terry?
Terry's currently indisposed. Oh, here he is.
Sorry about that. Alrighty, so what's next for the project? Well, I'm not sure if Mark and Joel covered, but look, what we're aiming to do is to get our payloads even lighter, our telemetry rates higher so that we can get more useful information down, and to get our battery life up as well. We currently get about 24 hours out of our payloads normally. We want to get more than that so that we can do even more with them. We've also got some work in progress in getting a Linux-based payload up in the air. So we're looking at doing something based on a Beagle board or a Beagle bone, but we need to do a bit more testing in harsh environments to see how that's going to go first. We're not quite there yet. And as you can see on the image here, Internode, who are actually sponsoring this event, have been kind enough to offer us some assistance in getting some node ponies up in the air. So keep an eye out for that. Hopefully we should have something back on that very soon. There's a few links up on the thing now. If you have laptops, you feel free to check them out. There's the project website, our tracking system, which certainly I would suggest having a look at now because there's going to be a balloon on it in the next few minutes. Some code repositories, our video channel where there's plenty of embarrassing footage of us. And a couple of blogs for the other team members there. So if you're happy to hold on for a couple of minutes, we're going to get the balloon ready to go. We're going to walk it out to the field just, I think it's behind this lecture theatre. If we could just ask that people stay in their seats until we're out of the door, and then feel free to follow us. So we're going to take the balloon out into the field, string it all up. Once everyone's happy, we'll let it go. Thanks. Oh, sorry, just one more question there.
Is there a repeater on it?
No, the question was, is there a repeater on the balloon? And the answer is no, not on this balloon.
This is a
Sorry.
50-gram payload so that we can launch it quicker than...
Sure, yep.
First question, Mark
Bring the
mentioned
balloon
that
up.
the GPS receivers must have 3. Did you have to deal with any paperwork or anything to get those?
I'm going to let Mark and Joel handle these so I can get the balloon ready. Mark, you can answer that
These receivers aren't ITAR free. They will go above a certain altitude, they won't work above a certain speed. So most manufacturers implement, or they're meant to implement the regulations as if speed greater than 500 meters a second and altitude greater than 18 kilometers, drop lock. A lot of them implement it as an OR. So it means you lose lock above 18 kilometers.
Also, you mentioned that the APRS was a backup telemetry, but I could be wrong, but my understanding was that there might
The question was about using APRS as backup with Micronaut being configured for either RTTY or APRS. We fly 2 payloads. So we'll fly RTTY payload as the primary telemetry and APRS as a backup. Any more questions?
Yeah.
Yep.
What kind of Canon cameras are you using and how much do they weigh?
The question was what kind of Canon cameras are we using? I don't know the exact model. It's
Relatively cheap old ones. Terry could do the. There's also on the website has the deals. One of the PowerShots. A70 someone's.
A560 the camera was.
And did you ever consider any breathing apparatus for Tux?
We didn't consider breathing apparatus. No, we were very inconsiderate when it.
That was my question, whether they got the RSPCA's approval.
Yeah.
No, we didn't get the RSPCA's approval.
Keep that in mind.
For next time, definitely. That poor monkey as well.
Okay, before we do liftoff, please everybody give thanks to Terry, Mark and Joel for their presentation of Tux in Space. Absolutely fantastic stuff. And more earthly bound, we have one gold-plated penguin. We can't give you one for each speaker, but we do have one for at least the project itself. So would you... Thanks very much. There you go. Cheers. Thank you very much.